Hi everyone, my name is Jiasheng from the Small Artifacts Lab at the University of Maryland. I'm excited to present our work, Toucha11y, making inaccessible public touchscreen accessible. This work is in collaboration with Zeyu, Arush, Shah, Lazar, and Huaishu Peng. From self-service print station on campus to ID renewal in the Department of Motor Vehicles, touchscreen devices have been widely used in public spaces, especially during the COVID pandemic. However, due to the lack of accessible features, many touchscreen devices in public spaces can be challenging for blind people to access and operate. Current laws such as the Americans with Disabilities Act require touchscreen devices in public spaces should be accessible to blind people, and several lawsuits in the USA have compelled large companies to make their public touchscreen devices accessible as well. Despite these efforts, a large proportion of new and existing kiosks with touchscreens are still inaccessible to blind people. To better understand the current experiences, we interviewed 9 blind participants. In the interview, we asked them questions related to their experience with touchscreen kiosks and how they operate the touchscreen devices. The design of Toucha11y is also guided by the findings from the interviews. Based on the feedback, first, we noticed that the common practice for blind people who need to use the touchscreen devices is seeking assistance from other people or choose not to use that. One of the participants said, the common sense for blind people when we come across a device with a touchscreen is that it doesn't work for us. Second, there are a huge percentage of existing kiosks are inaccessible to blind people, even if they are told these devices are accessible. One person said, I was told that the ATM was accessible, but after I plugged my headphones into it, there was no clear instruction on how to do that. Third, participants expressed their concerns about their privacy. One participant shared their experience in the Social Security office, where they need to ask others to help them operate the touchscreen devices. The feedback from the formative study informed our design considerations. First, due to the inconsistency of accessibility features and devices, we will focus on simplifying the learning and interaction process. Second, our solution shall protect their privacy and enable blind people to use touchscreen devices independently. Finally, our solution shall help blind people to save their time. During the design phase, we wondered what if we could build a small device that helps blind people understand the content on the touchscreen. What if the device can also activate the touchscreen devices for blind people? And what if we can have a device that bridges blind people with inaccessible touchscreen devices in public spaces? Here, we present Toucha11y, a working prototype that allows blind people to use existing inaccessible touchscreen kiosks independently and with little effort. The key to make this possible are two innovations. One is an extended rail with 360 rotation features that can reach and activate arbitrary buttons on the screen. The second is the robot can understand its location on the screen by taking photos. Use Toucha11y on existing touchscreen devices is easy and convenient. First, blind users will place the boat on the touchscreen. The boat takes 3 photos at 30-degree interval and uploads them to the cloud server to calculate its position in the screen's coordinates. Through the Toucha11y mobile app, blind users can freely access and explore the public kiosk touchscreen content with the smartphone's built-in accessibility features, such as voiceover. Once the user makes a selection on the phone, the Toucha11y bot will locate the position of the correct responding button on the kiosk interface, extend the touch probe to the button's position, and then register the event for users automatically. The Toucha11y bot can reach various locations on a touchscreen and thus can help blind users complete different tasks. The Toucha11y system comes with 3 parts: the Toucha11y bot, a smartphone interface, and a server. The server serves as a bridge connecting the boat and users' smartphones. The server receives the photo from the boat to calculate the robot's location and sends touch commands to the robot. It also generated a user web interface and received users' input commands. In the next few slides, I will go through each part individually. So the Toucha11y robot includes a Raspberry Pi Zero as a microcontroller. A motor with a rotary encoder controls the robot's rotation. Another robot with IR sensors controls the rear extension. A 3D printed touch probe with conductive pin registers the event on the touchscreens. The onboard camera takes photos on the touchscreens and uploads them to the server to calculate the robot's location. The extendable reel can reach up to 700 mm with a 5 rpm rotation speed. The size of the robot is 50 by 70 by 93 mm, and it weighs 162 grams. The server has three main functions. First, the server receives photos from the robot, matches the photos with pre-labeled interface, and calculates the robot's position. Second, the server generates the web interface and sends them back to the user's smartphones. Third, a pre-labeled screen interfaces database stored on the server, which can be generated from crowded cells. Finally, a web-based interface loaded on the screen's smartphone, which optimized for the accessible tools such as a screen reader. Since the Toucha11y system is essentially an open-loop system, we want to understand the performance of our current working prototype. We conduct a technical evaluation including three parts: location accuracy, rotation accuracy, and extension accuracy. We collected 5 public kiosk interface examples, each screen size of 12 inches, 21 inches, 27 inches, and 40 inches. Each example represents different usage scenarios. We located 5 test points for each interface, 4 at the corner and 1 at the center. For each testing point, we first created a red circular mark at the desired screen location. We then placed the Toucha11y robot right above the red mark. The robot takes 3 consecutive photos of the screen with a 30-degree interval in between, and then calculates the robot's position. The calculated position is marked as green dots shown above. We repeated 3 times for each location, calculated the arrow distance, and recorded the data in the table. Overall, the Toucha11y robot can be used to locate itself on touchscreen interface with a mean arrow distance of 6.5 mm. Given that the size of the button on most touchscreen devices is 25 by 25 mm, it is sufficient for the Toucha11y robot to reach the buttons on the touchscreen accurately. However, we do see some areas and interfaces which don't have enough features for the Toucha11y to recognize its location on the screen. For example, point 2 in sample 2 and sample 5 have fewer features for Toucha11y to recognize. We follow the similar step on the rotation and extension accuracy evaluation. The average rotation error is 0.66 degrees. The error is primarily caused by the small backlash from 3D printed gears and human manufacturing errors. The average error for the extension length is 3.52 mm in both extension and retraction actions. The linear encoder pattern at the bottom of the reel is the main cause of the error. As we affix the reel with reflective tape at 2.5 mm spacing, the extension accuracy will not be greater than 2.5 mm. Reducing the space will improve the extension accuracy. We also conducted a user study to evaluate how Toucha11y supports blind users in using an inaccessible touchscreen interface. During the study, participants are asked to finish a T-ordering task. The task involves 4 steps. First, participants are asked to place the Toucha11y robot on the touchscreen. Second, participants need to find the correct T options from their smartphones. Third, participants choose the sugar level on their smartphones. And finally, they need to confirm the ordering detail and complete the transaction. All the participants were able to complete the T-ordering task. The average time of completion was 87.2 seconds. We also collected bigger-scale questions to quantify the result. All the participants agree that putting the Touch Ally robot on the touchscreen is easy, and they believe that the device could reduce their cognitive effort and protect their privacy. Participants also shared their concerns that were mainly caused by unfamiliar and the robot size. Participants mentioned, "I hope I can put it in the pocket and carry it out like a phone." To improve these concerns in the future work, we can reduce the robot size by replacing smaller microcontrollers. We can also deploy the device for long-term use in order to better understand and how blind users will use it. Since Toucha11y is a temporary solution to make inaccessible touchscreens accessible for blind people use in public areas, it also can be used to assist any people who have difficulty interacting with touchscreens, for example, people with motor disabilities. Also, we don't want the research on Toucha11y to be the excuse for technology companies to stop developing accessible kiosks. One of the participants said, "Toucha11y might have unintended consequences, that technology companies who build touchscreen kiosks would care even less about accessibility if they see this robot is so cool and using the phone and your app is not difficult at all. Instead, I wish more technology business would begin updating public kiosks with accessibility features." Thanks for watching.